back for talk number 2, but we're going to start with continuing the numbering from talk 1, because I wanted to say one more bit from that talk, and this will connect a little bit to Achim's talk and also to what I'm going to say in the rest of talk 2. So in talk 2, as in right now, I want to explain why there should be some connection between Hochschild homology and these objects with S1 action and something involving cohomology, i.e. de Rham cohomology. And so I'll explain a bit of that story right now. And so to sort of set the scene a little bit, let me talk about trace methods and just say the following. As part of our scheme of desperation, we can't compute K-theory, so we're going to give up and try to compute some other things. And there's a long history to doing this, first to mapping to Hochschild homology, which turns out to be useless, and getting closer and closer to this. And so for much of the last 40 years or so, TC has been the best possible thing to put here. Maybe now one could argue that Selmer K-theory gets you just a little bit closer to where you want to go. But for us, we'll do TC. And really, I'm just going to be interested in TC with p-adic coefficients, so p completedly. And what is this? We saw a little bit last time. So first of all, and I'm going to get to some actual definitions later in this talk. So first of all, you start with THH of your ring, and we'll see so we saw a definition last time. I'll give another definition this time, and this comes with this cyclotomic Frobenius to THHR Tate CP, and now, as long as we only care about P completion, I can hit this map with homotopy S1 fixed points. And this is p-adically equivalent to THH R Tate S1, and that's TP of R. This is TC minus of R. There's also, so this is the cyclotomic Frobenius. There's also a canonical map just given by the map from the homotopy S1 fixed points to this Tate construction. And TC is defined to be the fiber of the difference between those two maps. So TC minus R can minus phi TP of R. And so it's some sort of Frobenius eigenspace. Okay, so that's a little bit about what's going on here. I'm going to say something about S1 spectra with S1 action in general in a moment, and also about this sort of homotopy orbits and Tate construction and so forth, for those who haven't seen it. But I want to give a kind of overview of how this fits into the story of prismatic cohomology and K-theory right now, really quickly. Okay. And and specifically how we're going to get a motivic filtration on these. So here's the definition. So a ring R is quasi-centomic, and here it's P. It's sort of, this is with respect to the same prime that Achim chose. So it's P quasi-centomic if it has bounded P power torsion and, well, it's really just two conditions. And the cotangent complex of R over ZP has P complete Tor amplitude in the range 0, 1, homologically. this basically means that if you base change this complex to R mod P, it has homology in degrees 0 and 1 and is sort of a complex that you can resolve by two flat R mod P modules. Yes? It's right. It's a possibly infinite version of a complete intersection. Mm-hmm. Yes, exactly. So certainly over ZP, any actual complete intersection would be quasi-symptomic. Thank you. So that's what quasi-symptomic means, and so these are yeah, okay. Bounded p power torsion is omittable, but you would have to allow derived or animated commutative rings into your life at some point. So okay, a ring is perfectoid if it is isomorphic to the Witt vectors of R flat mod D for some perfect FP algebra R flat and some D where this delta operation is a unit. So this is the delta operation coming from the Witt vector Frobenius, as we saw in Achim's talk. So this is sort of a, well, okay. This R flat is not random. You can build it out of R, but this is a fine definition. So in particular, any perfect FP algebra is such, but so perfect. And just because we haven't said it, any perfect FP algebra has a Frobenius, sending x to x to the p. That's a ring endomorphism. And an FP algebra is perfect if that ring endomorphism is an isomorphism. So this is one class of examples. The other class of examples is OCP. This is the ring of integers in the p-adic completion of the algebraic closure of QP. And I don't claim that the fact that it's perfectoid is obvious, but maybe it is to you. So the third is R is quasi-regular semi-perfectoid. Really rolls off the tongue and the chalk. If, so one, R is quasi-symptomic, I'll just write that is in Q sin. I'll call this Q sin, the category of such commutative rings. Oh, did I miss something? Sorry, people, for me, right, it's P complete. I want these to be P complete. Man. Bounded. And yeah, okay. So it's quasi-regular semi-perfectoid if it's quasi-symptomic. If it admits a map from a perfectoid, and then the third condition is that the cotangent complex of R over ZP has P complete Tor amplitude in 1, 1. In particular, that means if I suspend it down once, it's p-adically a flat R module. And you can see that you can see using the conormal sequence for the cotangent complex that any ring of this form does have this property on its cotangent complex. So perfectoid rings are quasi-regular semi-perfectoid. What's an example of something that's not? Well, ZP satisfies 1 and 3, but it does not admit a map from a perfectoid. So ZP is not perfectoid. It admits a map from a perfectoid. Any map from a perfectoid ring. A map of commutative rings. So like any FP algebra, so any characteristic P commutative ring which satisfies this condition would be quasi-regular semi-perfectoid. Well, no, commutative ring map. One goes to one, yeah. That's it. That's it. No, I mean, yeah. No, it's okay. Thanks for your question. Okay. Okay, so this is a class of commutative rings. Yes, thank you. Yeah, we allow arbitrary maps between these. And then quasi-regular semi-perfectoid will be mildly shortened to in this way. So what's the point of isolating this particular class of commutative rings? So we can make these we can make the opposites of these into sites using the p-adically faithfully flat topology. So make into sites with p faithfully flat maps. Which in the case that everything is torsion free just means that the maps mod P are faithfully flat. And one of the great observations of BMS2, which perhaps at least once I should say, this is Barkov Bott, Matthew Morrow, and Peter Schultz, is that sheaves on quasi-symptomic rings are the same as sheaves on quasi-regular semi-perfectoids. Okay, it's a statement about the equivalence of topoi that you get in this way. And so there's, in particular, a map. It's an equivalence. There's a map this way, which they call unfolding. And so this one, the P completely faithfully flat topology. And they use this to construct filtrations on TC and TC minus and TP by constructing them first for quasi-regular semi-perfectoids and then applying this unfolding condition, which is really a right-con extension. Okay, so the recipe is basically, you can compute it as some big limit, similarly to what Achim was saying. So let me just give you a tiny taste of how that looks. Yeah, definitely. Thank you. Yeah. So this is how it goes. So let me explain just very briefly how to get the motivic filtrations on TC minus and TPR. Okay. Okay. Yes. Okay, it's certainly true for sheaves of sets, and I'm sure it would be true for any sheaves of truncated spaces for any n. If you ask me if it's true, like some question about hypercompleteness or something, I'm not sure I know the answer off the top of my head. Maybe someone else here does. Okay, so now let me just give you a construction that relies on a little bit of belief, which is that now the main fact is that for R quasi-regular semi-perfectoid, TC minus R and TP of R are even. What does it mean even? It means, just to be totally clear, that the odd homotopy groups are 0 for all I. Okay, I'm allowed to put either of these in that box. Okay, so these are concentrated in even degrees, And that means that I can construct functorial filtrations on these. I mean, this definition would work in general, but I can define the motivic filtration on Tc minus R. It's going to be the double speed Postnikov filtration of Tc minus R. And I can do the same thing for Tp of R. For our quasi-regular semi-perfectoid. Okay. So these are, there's not much going on. I'm claiming that these are even, and we saw one example of that in the previous talk. For FP itself, THH is even, and then the homotopy fixed point and Tate spectral sequences just have to collapse, and there's only possibly contributions in even degrees. And that's the only computation one needs to do. All other cases that are quasi-regular semi-perfectoid are reduced to that, okay? The reduction is not completely clear. You first of all, maybe I just bring this back here. You first of all use this perfectoid, and it's not. It turns out that THH of these perfectoids just has also this Bachstedt periodicity. It looks like THH of FP. Okay, and then you work relative to that, and okay, I don't want to. I'll come back to this. So basically, THH of perfectoids. Perfectoid S is isomorphic to S adjoin the same element X from Achim's talk, okay? And then what you can do is you can mod out by that X. Modding out by that X, then, so THHR is a module over this, and THH mod of R modulo X turns out to be the Hochschild homology of R over S. And then under this cotangent complex condition, you can show that this is even. And I'll do that later in the talk, okay? So that means that this is even, but this X is in degree 2, so that must have meant that THH R itself was even, and then homotopy fixed point and Tate spectral sequence gives you evenness there. Okay, that's the bird's eye proof of the proof of that fact. Okay, that was very fast and mostly in words. Are there any questions? Was that serious? Okay, it was serious. Yeah. So the idea is first. So any quasi-regular semi-perfectoid admits a map from a perfectoid. That's part of the conditions. THH of a perfectoid S satisfies this Bachstedt periodicity. And so THH of R, which is what we care about, that's our general quasi-regular semi-perfectoid, it's a module over THH of S. And so I can mod out by X, this class X, and it happens that I get Hochschild homology R over S. The cotangent complex of R over S is also concentrated in degree 1, 1. And so that actually means that this is even. I'm going to do that calculation in a little bit. And so then unwinding, you find that THH of R is even, and then the same thing, that must mean TC minus and TP of R are even by the spectral sequences. Okay, that's the bird's eye picture. Yes? Yep. Yeah. Yep. It's cooked up. It's the special sauce. It's the family recipe that makes everything work. I mean, there's some sort of infinite dimensional LCI rings. But the point is that we need infinite dimensionality for some of the descent results. Okay? So I'll try to give an example in just a second. Okay. So now that we have this, I get a functorial, so I've sort of done a little bit to justify the claim that these are even, okay? And now, I mean, I could have written down this filtration, whether or not they were even, right? It just would have maybe, it wouldn't have been what we wanted to do, okay? So now we can unfold and apply that. And it turns out that TC minus and TP are actually sheaves. So I guess these must mean sheaves of spectra, but okay. They are actually sheaves in this completely faithfully flat topology. And so since they're sheaves, what I can do is I can unfold the filtration. Okay, so this filtration is functorial in the ring, so I get a sheaf on the site and I can unfold it, and unfolding, we get prismatic. We get the sort of motivic filtration on TC minus blank, and TP blank in general. And here's what it turns out the teeth-graded piece is. In general, well, it's just some symbols right now, but it's the teeth, the more than or equal to T part of the Nygaard filtration on Nygaard complete absolute prismatic cohomology of R, shifted up by 2T. And similarly, if I do this for TP of R, this is the Nygaard complete, oops, and I'm missing a Broykissen twist, it looks like. Sorry. Okay. So this is a claim, and I'm going to try to justify in this talk why there should be any relationship between these sort of homological invariants and something that is based in the end on de Rham cohomology. Okay. Okay. So let me just conclude this part of the talk, which with a recipe, how do we compute for something like FP adjoin X? Well, is FP adjoin X quasi-regular semi-perfectoid? No, it's not. It admits a map from a perfectoid, right? We have FP mapping to it, no problem, but the cotangent complex is wrong. It has Tor amplitude, over ZP in 0, 1, right? So no chance. So what do? We find a faithfully flat map from it. This is a faithfully flat map. Now this is perfectoid. In fact, this is just perfect, and that's certainly quasi-regular semi-perfectoid. And so then we do faithfully flat descent along this map. So let's call this R. Let's call this S0. And now we just take the check complex, S bullet, right? So I'm writing down the check complex of this map. The next one is S0 tensor R with S0 and so forth. And let me call this cosimplicial commutative ring S bullet. Each of these terms, it turns out, is quasi-regular semi-perfectoid. And so then what you do, the recipe, for example, to compute FP star of TP of R is you take the limit of the double speed Postnikov filtration of I only did one speed, of TP of S bullet. Each of these turns out to be quasi-regular semi-perfectoid, so these are all even, and we take this limit, and that gives us this motivic filtration. Okay, that's not like the sort of thing you're going to now just go and compute, but it is something. Let me just mention, I see a question, let me just mention one other quick thing here. What is this ring, S0, tensor S0 over R? This is like FP adjoin X to the 1 over P to the infinity, Y to the 1 over P to the infinity, modulo X minus Y. In particular, it has a ton of nilpotent objects, which is why we're like fundamentally leaving the smooth world when we're doing this descent and why you can't just do smooth stuff. Okay, question? Yeah, just because it's sort of canonical, these are just equivalent, in particular, like sheaves of filtered E-infinity ring spectra just are also the same on both sides. It transfers this obviously multiplicative filtration into some multiplicative filtration. Good question. Okay, I don't know. And any other questions? No, yeah, there's probably a good answer to that. It is the even filtration. But that's talk 5. Let's come back to that later in the talk. Yeah, I mean, just manifestly, it'll just turn out not to be even. It'll just turn out not to be the even filtration. It's because we're taking we're taking a limit of a bunch of things. Say you just have, say, GR 0, right, is just something in degree 0, homologically degree 0. Now I take a limit of a bunch of those things. Well, that limit can produce negative homotopy groups. aka that's where cohomology comes from. Well, it's they're somehow on different sites though. Yeah. It might. It might. Okay. Good questions. Any others? Yeah. Yes, and I'm going to skip that even harder now. What? Yeah, I'm. Let's. Yeah, I don't think we're making any claim about hypersheaves. This is a claim just about sheaves, sheaves of spectra, but not necessarily hypercomplete sheaves of spectra. What? Okay, let's. These are technical things for people who know a lot about this already. Let me try to move on with the rest of the talk. Okay, so now let me switch gears and talk about Hochschild homology. So Hochschild homology and objects with S1 action. And I want to give another perspective, a not descent perspective on this connection between Hochschild homology and de Rham cohomology. So very quickly, what is a spectrum with S1 action? Well, that's for us, it's going to be spectra BS1, which is just by definition going to be functors from BS1 to spectra. And this is a path-connected space, and so basically any point over here is the spectrum with S1 action. And how much do I really want to say here? I want to say just a little bit more. So actually, I'm going to talk just about Hochschild homology. So let me, in fact, look at complexes or Z-module spectra with S1 action. And let's think a little bit about this category. So Thanks. Let's think a little bit about this category. So I have a map from a point to BS1, and that gives me a pullback map from okay, well, this I can say in this generality, fine. X upper star, which is just forget the S1 action. And this has a right adjoint and a left adjoint. The left adjoint is given by X lower shriek, the right adjoint by X lower star. And because this forgetful functor has a further right adjoint, it preserves all limits. That means that X lower shriek preserves compact objects. X upper star is also clearly conservative, so that means that X lower shriek takes a generator here to a compact generator here. And so that tells us that this is modules modules over endomorphisms in spectra with S1 action of X lower shriek of the sphere spectrum. This is basically, and this is spherical chains on S1. Okay, this is the free induced object, induced representation. Okay, so this is just a sort of standard modules over this in spectra. This is a just standard derived from Morita theory argument here. Or if we did this for complexes, we find that this is the derived category of chains on the circle. This is some E1 ring spectrum, or in this case, E infinity ring spectrum, which computes the homology of the circle. In particular, the homology of ZS1 looks like Z join B modulo B squared, where the degree of B is 1. And if you think about what that means, one kind of, if you have M inside D, a Z module spectrum with S1 action, then on its homology, you get multiplication by B maps that go up. And square to 0. Okay? So if you have a spectrum with S1 action, the fact that sort of you can view this as a module over chains on S1 means you have this particular structure on the homology of M, which is the structure of a cochain complex on the homology. Okay? Now let me define Hochschild homology in a different way. Achim gave a hands-on definition, but let's let K be an E infinity ring. And now I'm going to look at the following. I'm going to look at E infinity algebra objects in K module spectra with S1 action, which, by the way, is equivalent to E infinity K algebras with S1 action. I have a forgetful functor from here to E infinity K algebras. And this is just forget the S1 action. And this admits a left adjoint called Hochschild homology. Left adjoint. Okay? This tells us the universal property if I have a K-algebra R and I have a map from R to some S, another K-algebra where there's an S1 action. So I also have a unit map of this adjunction. So there's a canonical map from R to here once I've chosen a base point. This is kind of forgetting, taking X upper star in the notation from over there. Then I get a unique S1 equivariant map here. Okay, so that's kind of the nature of this object. And then just sort of more notation, THH of R is Hochschild homology R over the sphere spectrum. I said I was going to define the Tate construction, but maybe I will skip that. So one of the basic theorems, and really the theorem that gets everything off the ground, is from Hochschild, Constant, and Rosenberg, abbreviated commonly HKR, from 1962. And what they did is that, so if K to R is a smooth map of commutative rings, then they computed the Hochschild homology groups. In fact, there are natural isomorphisms, omega T R over K, the differential T forms, into the degree T Hochschild homology. And these are isomorphisms for R smooth. In order to construct the map, you can do that for any commutative ring. And the way that you do it is that the Hochschild homology groups, well, it's a graded commutative ring, but it also has this differential coming from the S1 action. So that makes it into a commutative differential graded ring. And then the universal property of the de Rham complex, is that maps from the de Rham complex into a CDGA are equivalent of just giving maps from R into the degree 0 part of the CDGA. So degree 0 Hochschild homology is easily seen to be R. And so you get a map like this. And then to prove that it's an isomorphism for R smooth, you can eventually reduce to the case of a polynomial ring in one generator and just make that computation. Because both sides are basically sheaves in the Étale topology. Okay. So this is the theorem, and then Laudet proved, kind of justifying a little bit, that the action of this B operator under this isomorphism is, well, what could it be on here? It's the de Rham differential. Okay, so this part, as far as I know, is due to Laudet, and it's in his book on cyclic homology. So let me give a little bit more notation. So HC minus R over K, this is HHR over K, homotopy S1 fixed points, HPR over K is HHR over K Tate S1, and so on and so forth. Now we want to construct the motivic filtration on negative cyclic homology and periodic cyclic homology. And I'm going to do so not by quasi-symptomic descent, but rather somehow by some other tricks that use at heart this fact here. So to sort of justify that, let's remember how it looks, the homotopy S1 fixed point spectral sequence. So let me write it out. E2 ST. So this is going to be, in this case, it turns out to be the following. It's the degree S cohomology of CP infinity, or BS1, with coefficients in the minus T forms, R over K, and then converging to negative cyclic homology in degree minus S minus T, R over K. Okay. And again, the differentials are just R and 1 minus R. So now let's write this out. So when T is 0, this is just R itself, and I get the cohomology of CP infinity. So that looks sort of semi-two periodic, just as in Achim's talk. And then when t is -1, I get omega 1 here. And then again, this is 2 periodic, semi 2 periodic. Would that be 1 periodic? Okay, and omega 2. And now which way do the differentials go? Okay. I just want one more here. Well, the D2 differential goes like this. And it turns out that this D2 differential is the same as this de Rham differential, and hence, coming from the B operator. And so this sort of idea, well, okay, so this is the E2 page of this spectral sequence. That means that the E3 page has on it the de Rham cohomology groups, right? We're in the affine case. Oh, yeah, sorry. Okay. Yeah, Lars is absolutely right. Except here, where we'll just have cycles. Or cycles. If we were to do Tate, we would continue this sort of periodically in this direction as well. So this way is Tate. Thanks. And so the E3 page looks like de Rham cohomology. Okay? And now I want to explain one way of taking that observation and actually building a functorial filtration on negative cyclic homology where you do get de Rham cohomology or cycles. Okay. Any questions before I do? No questions? Okay. So the basic idea of how to turn this into something kind of coherent is to use this old idea of décalage, and the so-called Bailenson T structure. Well, this is one way to do it. So décalage, in the case, this goes back to Deline's Hodge 2, and it's just a way, if you have an actual filtered complex, of producing a new filtration where the E1 page of the new filtration is the E2 page of the spectral sequence of the old filtration. Now that construction is very explicit, and it's about like actual filtered complexes, not objects in these derived categories. And so this Bailenson T structure gives a way of implementing that décalage in this sort of more homotopical setting. And so what is it? So okay, we're working, well, whatever. Let's just say filter derived category of K. So this is functors from Z op into dk. This is the infinity category of decreasing filtrations. Looking just like FIM, FI minus 1M, and so forth. And this has many different T structures. Like, for example, you could just take the pointwise T structure, where an object's connective if each Fi is connective. The heart of that T structure would be just filtered K modules. So let's not do that. Let's take the Bailenson T structure, which is defined as follows. So the connective objects in the Bailenson T structure. So these are filtered K-module spectra with the property that each GR-I is minus I connective in the standard T structure on K. And the co-connective objects are the filtrations where FIM is minus I co-connective. Note the asymmetry here. We're giving on here a condition on the graded pieces, on here a condition on the filtered pieces. And it turns out that the heart of this T structure is equivalent to the abelian category of cochain complexes on K. Okay, cochain complexes is an abelian category. Usually we invert quasi-isomorphisms. Here we're not inverting quasi-isomorphisms, and so that's an abelian category. What's the recipe for going from something in the heart to here? Well, it turns out that if you're in the heart, then GR-I of M is inside dk sort of minus I to minus I for all I. And so then when you unfold, anytime you have a filtration like that, like this, you have maps like this, whose compositions are null homotopic. This sort of canonically has the structure of a sort of so-called coherent cochain complex by work of Stefano Ariata. Anyways, when you do this, what you see is that each of these objects is discrete in some degree, but when you unwind this, they end up being discrete in degree 0. And the compositions being null homotopic mean that the differentials square to 0, aka it's a cochain complex. That gives us a functor from this way to this way, and that functor turns out to be an equivalence. Okay, so that's the Bailenson T structure. Now you can ask, what is, if I have a filtered complex, what is pi I or pi t in the Bailenson T structure? It's precisely some line in the E1 page of the spectral sequence. Okay, so what is the spectral sequence? How do you get the spectral sequence of a filtration? Well, first of all, the E1 page is just the homology of the graded pieces with the differentials exactly induced by these connecting maps. So what you do is you take this and you just hit it with pi I, and that gives you some cochain complex. So that's one of the rows in the spectral sequence. Okay, and that's the teeth homotopy object in this T structure. So what are we going to do here? Well, here we exactly have I guess I indexed this as an E2 spectral sequence, but we could have done it as an E1 spectral sequence. So what are we going to do? So let me make the following convention. So if I have a cochain complex, so maybe n dot, a cochain complex, then bullet n will be the underlying object in the derived category. And in this case, I have this, okay, right. So, yes. It's some line in the E1 page of the spectral sequence. I guess the standard thing is it would be the teeth row in the E1 page. Okay, sorry, I think I need to say a little bit more. So the HKR filtration of Hochschild homology is just going to be the Postnikov filtration for R smooth. And so that means that GER T is going to be the differential forms in dimension T. That's another way of, this is another way of expressing the HKR theorem, and this is natural in R. The fact that it's natural in R means that we can left-con extend this filtration from smooth K-algebras to all commutative K-algebras, or even to all animated commutative K-algebras. So the left-con extension gives you a filtration on HKR of any animated commutative ring R in animated commutative K-algebras. And here, what is the teeth-graded piece? Well, when we derive the differential T-forms, what we get is, the teeth exterior power, the derived teeth exterior power of the cotangent complex sitting in degree T, or we could just write that as L omega T R over K sitting in degree T. I just did. Sorry. Thanks. The question was, have I defined F star HKR? So now, okay, what am I going to do? I want to define a new filtration on negative cyclic homology. So I get an HKR filtration on negative cyclic homology. Algebraic. The question was, is this the algebraic cotangent complex? The answer is yes. So I can take the HKR filtration. So this Postnikov filtration is S1 equivariant. And so what I can do is I can just take this filtration and hit it with homotopy S1 fixed points. I'll do this R smooth again. Tau more than or equal to star, Hochschild homology, R over K. All of this Postnikov tower is canonical, and so it's still S1 equivariant, and so I can hit this with homotopy S1 fixed points. This is the filtration which gives us this spectral sequence. Okay, that's one way to think of that. And now what I can do is I can take the Postnikov tower of this. Oh, of this one, or do I want a 2-star here? I think I want a 2-star. I can take the Postnikov filter. This is a filtered complex, so it's an object in the filtered derived category. And so I can take the Postnikov tower in of this object as an object in the Bailenson T structure. And what do I get? So the graded pieces of this, if you think of what they are, the graded pieces are cochain complexes shifted in some degree, because the graded pieces are objects of the heart. Okay? But, and this, maybe another point is that this is 2 filtrations, right? This is a filtered object in filtered objects. Most people's heads break at that moment, because it gets very confusing to think about these bifiltered objects. So we want to forget one of the filtrations. We want to forget the internal filtration coming from here. Okay? So when we forget the internal filtration, I guess I need more board space. When we forget the internal filtration, we now have a tower Oh, sorry, I think I forgot to put this on here, so I'll just stand here for a second. Yes, exactly. By forgetting the filtration, you're taking a colimit. Forgetting the filtration is kind of going to the colimit as I goes to minus infinity in that picture. And now there's a question of which direction you want to forget the colimit in, and it's in this internal one. And what that has to do on the graded pieces, those are cochain complexes, and that's exactly take the underlying object in the infinity category. That's the cochain complex, and the filtration is sort of the stupid filtration that you have on any given cochain complex. So the claim now in this smooth case is that in this filtration that pi 2I b of f star HKR HC minus R over K. So this is some specific cochain complex. And what cochain complex is it? It's exactly, so this is an isomorphism in a one category. So it's the same as the following cochain complex. It's omega I R over K, omega I plus 1 R over K, where this starts in degree I. Or minus I. I'll just say plus or minus I. We'll figure it out here. This is a specific cochain complex. That means when I take the underlying object, so this notation will also mean underlying for the filtration. This means that when I take the underlying object, so I have this tower, each of these okay, I'm just going to write box for this. It's going to be too long. So each tau more than or equal to 2I, this is a single filtered complex, and I can take the underlying object here. So this is a new tower of objects in the derived category of K, i.e. it's a new filtered complex. Okay, this is a new filtered complex. That's exactly what I mean by forgetting the internal filtration here. And this analysis tells us that when I take, so this is a new tower, and I'll call it F star mote of HC minus R over K, as opposed to this kind of silly filtration which we get by just taking the HKR filtration and taking homotopy S1 fixed points. Okay, this is different, and what is gur I of this tower? Gur I mote of HC minus R over K. So it's exactly the complex underlying these cochain complexes. Okay, and that's Fi Hodge. It's Fi Hodge of the de Rham complex of R over K, shifted by 2I. So Fi, I'll leave that there. Fi Hodge, right? The de Rham complex in this, we're still in the smooth case. The de Rham complex is an actual complex, and like F1 Hodge would be this one. So we're not starting with R. F2 we would delete omega 1 and 2 and just start there. And so when you kind of work this out, what you're seeing is that this is exactly a new filtration on negative cyclic homology, which has effectively turned the page in the spectral sequence. But it's done it in a totally coherent way that works, completely functorially. Okay? And it produces these graded pieces really as objects in the derived category. So, sorry. So I should have taken out the dot. Sorry. That's an important point. I don't mean that it's any longer still the actual de Rham complex. It's the underlying object of the infinity category that this computes. Okay. What was the question? The FIH depends on the chain complex, but FIH omega is just an object in the derived category. Right. It's the, yes, okay. Is that what it means? Then yes. Okay, so very briefly, this effectively gives you a filtration here, and now you can left con extend this in an appropriate way to get motivic filtration on HC minus R over K, and a motivic filtration on HPR over K for any R, for any animated commutative ring R. And here GR I, in this case, will be this Fi Hodge of the derived de Rham cohomology. I'll just write de Rham R over K, and there's a subtlety. It needs to be Hodge completed, shifted by 2I, and in this case, GR you just get, it's two periodic Hodge complete derived de Rham cohomology. This left con extension is a little subtle, but these filtrations will in general be complete, and they'll be exhaustive under some quasi-LCI-ness conditions, okay? Now there's two other ways of getting these filtrations based on work of Arpan Roxet. I was gonna talk about this, but I definitely don't have time, and Molinos Roballo Toen give sort of other higher brow approaches to this, but I wanted to sort of explain one hands-on way of making this specific connection between Hochschild homology and negative cyclic homology and periodic cyclic homology and de Rham cohomology. So I'd better stop there. Thanks. Right. The question is, why do I take the double speed Bailenson Whitehead Tower? And it's because, like in this picture, if I took the single speed one, a bunch of them would be like 0 lines interspersed here. So we'll just skip those for the same reason as we skip them in other. This thing is, for smooths, this is Bailenson even. Good way of putting it. Thanks. Right, so this T structure, so the question is, what would have been different if instead of working with the derived category of K, I worked with spectra? So there's also a Bailenson T structure on filtered spectra. It's the exact same thing. The heart is also cochain complexes of abelian groups. But I guess the question is, so that works. Now, if you instead wanted to do THH, I think that's where it would start to get a little trickier. So somehow, well, there's also a question of which category, right? Here we're, if you wanted to do E-infinity rings or whatnot. Here, what we're really using is the fact that for smooth K-algebras in the discrete case, we have this very nice description of Hochschild homology. And there's just not a way to do that over the sphere that somehow appropriately filters out the differential forms data from the homotopy of groups of the sphere data, as far as I know. So there may be something intelligent to say in that direction, but I'm not sure what it is. Yes? So R is smooth on this board. And then we left conextend these filtrations. So this motivic filtration on negative cyclic homology, we left conextend from R smooth to all animated commutative K-algebras. It could be a definition, but it's a statement. The issue is that the left conextension has to be done in an appropriate category of complete filtrations. And that's why you end up getting Hodge complete as opposed to general derived Durand cohomology. Hat means Hodge complete. So specifically, right, so we haven't mentioned this. Very briefly, I'll say, I have Durand cohomology, which just, I have a smooth K-algebra. It spits out the underlying complex of omega bullet R over K. Okay, that's Durand R over K. And this has a filtration, the Hodge filtration. Now, if we left conextent, so for a smooth algebra, this filtration is complete because eventually the differential forms are just 0. But if we left conextend it, it's no longer, from finally generated polynomial rings to general rings, it will not be complete in general. And so we just formally complete it by letting dr hat be the limit of dr mod fi. Okay, and that defines Hodge complete derived Durand cohomology. Or if you like, alternatively, it's just simply the left conextension in complete filtered objects. Yeah.
Explain again how doing this filtration Benson filtration
Changes the page? Well, right. So the question is, why does this Bailenson filtration sort of implement page turning? And so pi t Bailenson is a cochain complex, and it's exactly the E1 page, one of the rows in the E1 page of the spectral sequence. Okay. Now, this operation of sort of taking the underlying, forgetting the internal filtration, means here we forget the cochain complex structure. That means we're now viewing this just as an object of the infinity category. And now what's the E1 page of this spectral sequence? That involves the cohomology of this object, the homology of this object. Well, that homology of this object is exactly what we get by computing, kernel mod image on the E1 page. Thank you.
No, I don't. You did? Okay, then I think we can just leave it here.
Okay, do we stop the recording?